If you think about breakthrough efficiency versus performance, we can, in a simplistic manner, plot software 1.0 flexibility, so standard general purpose computing, lines of code as we talked about, or we talked about sparse matrix computations. You can implement that with a standard code, for example. That's your software 1.0 flexibility. Most general purpose processors are very good at that. And then on your y-axis, we're looking at efficiency. While we can do that flexible programming, how much efficiency, typically measured in performance per watt, or at the fundamental level, energy per operations, and then you have operations per second, so you get energy per second, so to speak. In the language of AI, we would measure this in performance per watt. When we started focusing on this, we realized very quickly that if we were to build silicon for AI, which is essentially software 2.0, that is nothing but a data flow, as we saw. It's essentially a graphical structure where there are interdependent relationships between your data as well as the operations that you perform on that data. As we saw, if you recall, in the first or second slide with transformers, that's our core mission as a company. To essentially build software-defined, software 2.0 specific acceleration, where we can now achieve orders of magnitude more power efficiency, speed, or lower latencies, as well as your cost ultimately reduces significantly. If your heat dissipation is lower, your power is lower. Of course, if you're building software 2.0 specific architectures, it's not enough if you want to build a scalable solution. So next we looked at where is the bottleneck of AI? And it turns out data is the new oil. Data is what is driving all these AI systems. And where is this data? This data is not really in your data centers. As you can see from the statistics here, 75% of enterprise-generated data is going to either be generated, created, or processed at the edge, whether that's edge of your network or edge of your devices. So if we were to move all that performance with better power efficiency closer to the source of data creation, we minimize or reduce all the energy expenditure that we have as a result of moving data. And that's where we concentrated on the edge. So we are bringing compute closer to the source of the data itself. And hopefully that should give us a lot more scalability to tap into all that data sources, distribute our computation across an edge landscape, and benefit a lot more in power efficiency and performance. A single unified platform in an industry-first manner where you have software all the way to silicon, where the software was designed to work across the heterogeneous landscape of processors. Whether you're mixing x86, Intel, AMD, ARM, RISC-V, you should not have to change your platform. And that system scaling mindset is what we now see as a single platform here that allows you to reduce the AI deployment time from multiple months to few days in the most extreme cases. We brought all of this together as a simple semiconductor, a simple chip, I call it simple, as an AI processor dedicated for software 2.0, but that gives you quite a lot of compute while consuming comparatively less amount of power consumption, which you can now dynamically trade off.
We can realize up to 60 trillion operations per second, or 30 teraflops of computing performance, depending upon at what level of precision you're processing.
And you're natively processing data in the order in which it arrives. In the language of machine learning or AI, we call this batch one, which is very different from what you do in data centers. And then fundamentally have flexibility in mind. Not create a silicon that only works for one type of AI application or model, but rather scales across vision as well as latest generative AI applications while preserving your power efficiency benefits. And then, of course, you cannot afford to trade off accuracy. So on the left-hand side, I'm comparing the size of such a software 2.0 specific processor compared to a same process node technology GPU. You'll see that we can achieve very similar compute numbers in terms of peak compute or teraops. But there's a big difference in terms of size. And we all know that die size has a big impact on cost. It also has a big impact on power. So while we can trade off the size of the processor, because you don't need to waste real estate for other general purpose things, you can now achieve very high performance per watt advantage, whether you're dealing with high resolution data or you're dealing with low resolution data. If you have the right mixtures, in our experience, of architecture, software, and you're able to co-design those together, even while preserving an older process node, in our case 12 nanometers, and you compare what we can get by moving to an advanced process node like 7 nanometer, we can still preserve considerably speed, in this example 4x better, as well as power efficiency, 7x better. This is just an example. There are applications where this gap can be as big as 20x in terms of power efficiency. And that is, again, inherently mechanisms that we can use as an industry to, again, deal with the Moore's law slowing down. What we learned in our own explorations was that it is possible to create architectural innovations, software innovations, designed for software 2.0 in mind, and create these edge processors as building blocks in a Lego-like manner that allows you to move a lot closer towards my zone of high efficiency.
SAKURA-II is the industry's most flexible and power-efficient generative AI accelerator for the edge. Our Edge AI platform enables customers to run a robust and diverse set of neural network models, from convolutions to the latest generative AI models, including multi-billion parameter large language models. SAKURA-II has a number of key benefits which make it ideal for generative AI, including support for multi-billion parameter generative AI models within a typical power envelope of 8 watts per device. SAKURA-II also provides highly efficient AI compute, achieving more than 2 times the AI compute utilization of other solutions, resulting in exceptional energy efficiency. With its enhanced DRAM bandwidth, SAKURA-II has up to 4 times more bandwidth than competing AI accelerators, ensuring superior performance for LLMs and LVMs. In addition, SAKURA-II has robust memory bandwidth and capacity of up to 32 gigabytes of 64-bit low-power DDR4X per device, enabling efficient processing of complex vision and generative AI workloads. Finally, with the real-time data streaming, SAKURA-II is optimized for low-latency operations with batch size 1. SAKURA-II is available for deployment in 2 major form factors: a small M.2 module, which is ideal for space-constrained designs, and a low-profile PCI card with single device or multiple device options, which is optimal for high-performance edge AI servers and appliances.
Hopefully, I've been able to give you some highlights in our own journey. I try to touch upon some of the fundamental challenges that we see, from software 2.0, memory, to even packaging. As a company, we have a new R&D center in Kanagawa, so I welcome you if you have the time to visit us and learn more about what we are doing as a young technology company in our endeavor towards the future of building silicon for AI. Thank you for your time.